Okay, it's time to talk about memory. Did you ever wake up one day and you just feel lousy? So sick to your stomach, maybe you got a flu, you don't really know. Just know that getting out of bed and heading to school is not going to happen. And you say, oh God, I can't be sick now. Now isn't a good time to be sick, because now is never a good time to be sick. But you have finals and you feel really terrible. So you call Dr. Levin and you say, Dr. Levin, I'm really sorry, but there's no way I'm going to make the final today. I just feel so terrible. And Dr. Levin, the kind and benevolent man that he is, says, oh my word, I hope you feel better soon. You should really rest. Why don't you stay home and not get anybody sick? You can take the final another day. So you go to bed and you sleep all day and you wake up around like 4 or 5 o'clock in the afternoon and you feel so much better. Like good enough that you want to go out to eat, have fun, maybe see your friends. And you're like, uh-oh, if I go out now, my friends will think I was faking. They might tell Dr. Levin on me if they're not great friends. So you stay home, you get some stuff done. The next day you go to school and everybody goes, oh man, I thought you were sick. And you say, oh no, it was just the 24-hour bug. That's all. Now I feel all better. Well, what exactly is the 24-hour bug? I teach microbiology to you guys, and I have bad news. I don't know what the 24-hour bug is. You know why? It doesn't exist. What you had was a perfectly normal, run-of-the-mill cold. For instance, the common cold, which is caused by rhinovirus, has 124 different types of rhinovirus. And so you could be infected with rhinovirus 124 different times, and every single time it would feel like a brand new one. But let's say that last year you had a really bad cold, and it was caused by rhinovirus serotype number 73. And let's say 2 days ago you were visiting a friend who happened to have rhinovirus 73, and you contracted it again from them. But instead of attacking the virus all over again with a slowly building primary immune response, your immune response remembered rhinovirus 73 and said, oh, we know what to do with this one, and started attacking it immediately, just as it started to reach the threshold when you felt kind of awful. So you felt really bad, you went to bed, and when you woke up, your memory immune response had taken care of everything. So that, my friends, is immune memory at work. Immune memory is a property of the adaptive immune response that has evolved to provide a faster and more specific response if we encounter a pathogen more than once. It will also be of greater magnitude. So your memory response has a more specific and quicker and higher response than your primary or first immune response. There are several key differences between the primary and secondary immune response. When you first encounter an antigen, you have a relatively small number of cells that have never seen the antigen before and therefore will require priming. This is a very small pool because we need to have a lot of diversity for the various antigens we could encounter in our lifetime. However, when making our effector responses, we expand the number of cells. So if we see the pathogen again, we now have an expanded pool of effector pathogen-specific cells that are ready to respond immediately. As I've mentioned before, the primary immune response and basically the adaptive immune response has a lag phase before it gets to work. So remember that your innate immune response is going to bridge the gap until the adaptive immune response is engaged. This time period between when you could be exposed to the pathogen and when antibodies are produced is referred to as a lag phase. In a secondary immune response, it is highly likely that you'll have antibodies that are still present in the serum capable of responding immediately. Alternatively, if it's been rather a long time since you saw that antigen, plasma memory cells or memory B cells that can differentiate into antibody-secreting plasma cells are present in the lymphoid tissue, ready to immediately start secreting antibodies upon activation. During a primary immune response, recall that IgM is always the first antibody made. Therefore, in primary immune responses, it's likely that a patient's titer of antibodies will show a higher amount of IgM antibodies compared to IgG if we're looking in the blood, or IgA and E if we're looking at mucosal sites. In the secondary immune response, though, we're looking at class-switched memory B cells. These will be of IgG, A, or E, not IgM. There really isn't any memory for IgM antibodies because you require T cell help in order to make a memory B cell. So really, we're looking at class-switched B cells that have become memory B cells that will eventually, if reactivated, make class-switched antibodies. There's also a difference in the pathogen burden that's necessary to create an immune response. In a primary immune response, you need a high pathogen burden before you'll even get any sort of immune response if this is your threshold where we will start making an immune response. Whereas in a secondary immune response, you actually need a relatively lower one. So if the pathogen amount gets much lower, to say here, we'll start making a secondary immune response. When if the pathogen burden stayed here during your primary immune response, you would not have made a primary immune response. As I mentioned before, memory B cells can only be induced in the presence of T helper cells. Specifically, T follicular helper cells are incredibly important in this. Because we need T cell help to create memory B cells, you do not get memory for B cells that are specific for T-independent antigens. There is no memory for the IgM secreting B cell. It's just never considered a memory response because they can't be recognized by T cells. So within the germinal center, or the follicles, you'll have T follicular helper cells, and you'll also have specialized dendritic cells, known as follicular dendritic cells. These follicular dendritic cells and T follicular helper cells can interact with B cells and induce a variety of responses. So just to not confuse you, remember that a B cell can encounter antigen freely, and if it encounters an antigen freely, it can differentiate into a short-lived plasma cell capable of secreting IgM, but those are not memory cells. However, if it gets antigen presentation and cues from the follicular dendritic cell and the T follicular helper cell, it can be induced to become a memory cell. Then, when you have a secondary immune response, this memory B cell can immediately become stimulated and create antibody and immediately get rapid plasma cell differentiation and quick increases in the serum concentration of IgG. Recall that the B cells, the memory B cells in the germinal center with the highest affinity for antigen will receive survival signals and begin to proliferate after receiving signals from your follicular dendritic cells and your T follicular helper cells. So in the lymph node, you have B cells being activated by a protein antigen. They get help from T follicular helper cells that induce class switching, somatic hypermutation, and higher affinity antibody. If you do not get T follicular helper or FDC interaction, the B cells will be short-lived and they won't survive very long. Remember that the secondary immune response is basically controlled by IgG, and this is because IgG can actually control the levels of IgM. This is actually done using the inhibitory receptor Fc gamma receptor 2b. Just as I talked about in the B cell peripheral tolerance video, this will ensure that low affinity IgM producing cells are being prevented from producing antigen because we actually want the IgG that is likely to be higher affinity, because that high affinity means it's going to have a better response. The properties of antibodies in the primary and secondary immune responses can be correlated to antibody responses that we see in immunized or vaccinated or unimmunized or non-vaccinated individuals. So for instance, in a patient that has never been vaccinated before or has never seen the antigen before, you're likely only to see an antigen-specific B cell occur once in every 1 × 10⁴ or 10⁵ B cells. Following vaccination or exposure to the antigen, that ratio goes way down to 1 in every 10 to the second to 10 to the third cell. So we went from 1 in 10,000 to 1 in 100 to 1 in 1,000, which is pretty good. This also means that, remember, these cells will have class switched, gone through somatic hypermutation, and they'll have higher affinity. If we're looking in a primary immune response, the affinity of antibodies is likely to be low, and they won't have had an opportunity to go through somatic hypermutation yet.